This is Euclid Book 10, proposition number 3. Here is the illustration. Okay. And it says, given two commensurable magnitudes to find the greatest common measure. Okay. Let the two given commensurable magnitudes be AB and CD. And AB will be the less. Okay, so we have AB, CD, these two lines are commensurable, but AB is not as long as CD. Okay. Thus it is required to find the greatest common measure of AB and CD. Now if magnitude AB either measures, now the magnitude AB either measures CD or it does not. If then it measures it, and it measures itself also, AB is the common measure of AB and CD. And it is manifested as also the greatest. For a greater magnitude than the magnitude AB will not measure AB. Now what does that mean? Okay. If AB measures itself, and it also measures CD, then there is no number greater than AB that will also measure AB. So therefore AB ends up being the common measure of both AB and CD. It also happens to be the greatest common measure. Okay. Next, let AB not measure CD. Okay, so now we're going to say that AB, when it measures CD, it leaves a remainder. That's what he's saying. When a line cannot measure another line, what it means is when you try to measure this line with this line, it's going to leave some kind of remainder. Okay. Then, if the less be continually subtracted in turn from the greater, that which is left over will sometime measure the one before it, because AB and CD are not incommensurable. And this is referring to Euclid Book 10, proposition number 2. So, let AB measuring ED leave EC less than itself. Okay. So, AB is going to measure ED, and when it does, it's going to leave a remainder called CE. Okay. Let CE measuring FB leave AF less than itself. Okay. That means is that we're going to take this CE here, and when we measure AB, we're going to have FB as the length, and there's going to be this little remainder of AF left behind. And let AF measure CE. So now we're going to take AF, we're going to measure CE. Since then AF measures CE, while CE measures FB, now at this point you're probably going to go, man, what is he talking about? Okay. We've now established that this line measures this line, and this line measures this line. Therefore, AF will measure FB. So AF will measure FB. But AF measures itself. So now we can say that AF measures itself, it also measures FB, without leaving a remainder. Therefore, AF will measure the whole AB. AF will measure all of AB. Because if it measures itself, and it measures this line without leaving a remainder, it'll measure the whole thing. But AB measures DE. Okay, so this line here measures this line right here. Okay. Therefore, AF will measure DE. Okay. This line here will also measure this line here, without leaving a remainder. But it also measures CE. Okay. Now we're going to say that AF measures CE. Therefore, AF measures the whole CD. AF measures CD. Therefore, AF is a common measure of AB and CD. AF will measure AB. AF also measures CD. I say next that it is also the greatest. For if not, there will be some magnitude greater than AF which will measure AB and CD. So now we're going to say that there is a line longer than AF that will measure both AB and CD without leaving a remainder. We're going to let that hypothetical line be G. Since then G measures AB, okay, now we're going to say that G measures AB, while AB measures DE, now we're saying that AB measures DE. Therefore, G will also measure DE. Okay, so now we're going to say that G measures this. But it measures the whole CD also. Now we're saying that G measures CD. Therefore, G will also measure the remainder CE. So now we're going to say that G measures this. But CE measures FB. Okay? So this measures this. Therefore, G will also measure FB. G will measure this. And remember, every time G measures a line, it leaves no remainder. But G measures AB. We said that G measures the whole of AB. And it will therefore measure the remainder at AF. G will now measure the remainder AF. Okay, so now we're saying that G measures AF. Now here's the problem. We already said that G is bigger than AF. Remember, we've said that 3 is bigger than 2. Now 3 is measuring 2. That doesn't work very well. Okay. Therefore, no magnitude greater than AF will measure AB and CD. Because if it did, then G here would be able to measure AF, and now we're saying that G is bigger than AF, but it's still able to measure it without a remainder. Ha! Wrong. Therefore, AF is the greatest common measure of AB and CD. Therefore, the greatest common measure of the two given commensurable magnitudes AB and CD has been found. Porism. From this it is manifest that if a magnitude measures two magnitudes, it will also measure their greatest common measure. What does that mean? Okay. In other words, if this measures this and this measures this, then see, if AF measures AB and AF measures CD, then AF will measure itself. That's what it's saying. Alright, I will tell you more in a future video. Stay tuned.